Hello, flat earth researchers, debaters, and debunkers. The belief that we live on a spherical earth has been derived from a mixture of geometry and trigonometry, giving us these orthographic or side on illustrations of us being on a spherical surface. However, no tangible measurements of curvature have ever been made. Instead, observations of objects in the sky, such as Polaris or the Sun, have been converted into this assumption that the Earth is spherical. But really, they work perfectly fine on a level surface when we incorporate the reality of the way we observe everything around us using the laws of perspective. So what we can understand has happened in the globe Earth belief is that observations have been made and they are always governed by perspective or the laws of perspective, which we can illustrate or talk about mathematically by using the inverse square law. Basically, the further away something is from us, the smaller it will appear in our field of view, and our entire field of view does that. That's why the surface and the sky appear to meet in our vision, because it's governed by perspective. And that's the same whether it's through a camera lens or a telescope or whatever. All our observations are governed by perspective, but that is totally ignored, or that is converted into this very uniform trigonomic or geometric form and then converted into a side-on illustration. So there's no denying, for example, that we can determine our latitude or location on the Earth based on the angle of elevation of, say, Polaris that we see in any given location. It works perfectly fine. It's just we understand that that apparent drop over distance of Polaris towards the horizon is simply because we've gotten further and further away. So the gap between the surface and Polaris just appears to get smaller and smaller. It's not because the Earth is spinning and rising up to meet it, or that we are having our view obscured by curvature. It's simply that we've gotten further away, so the size of the gap between the surface and Polaris is a lot smaller in our vision, and that's because of perspective. So really, you just have to understand that the level Earth and what we see around us is all from perspective. And of course, perspective has not been used when you use orthographic illustrations and geometry and trigonometry to kind of convert the observational view that we have from our own eyes. So let's just try and keep this really simple and start off with this image of a ruler here. And this would be similar to an orthographic view, right? It's a side-on view, and we see a very uniform distance between the 1, 2, 3, 4, 5, 6 inches. And okay, that's fine. It kind of works. Now, we know that we could take this ruler and we can measure a surface, and we can know for sure that it's say 3 or 4 inches across, or we could measure the height of something and know how many inches or centimeters it is. However, the first thing to keep in mind is that we are looking at a photograph of a ruler. So what we see is not real inches. What we're seeing in our eyes is not actually measuring 1, 2, 3, 4, 5, 6, 7 inches. We're just seeing a photograph of a measuring device, right? That's the first thing to bear in mind. But then if we go to this view, this is a good illustration of how we see the surface, or you could imagine this being us looking up at a tall building. We're at the base of the building and we are looking up to the top of the building. We get the same effect. So whether we are looking up into the sky or we are looking across the surface, This is the optical effect that we see. And this is, of course, perspective. Now, this is also why we cannot really know the true distance to the Sun or Polaris. Regardless of the angles that we can measure, we cannot actually know the distance because, as we can see from this, it becomes arbitrary. It's not uniform, so you cannot really convert what we see here into a side-on orthographic view with uniform measurements. So let's just illustrate that here to start with. Just very simply, what I've done here is I've just again we are looking at an image, but these yellow lines in the software are each an inch apart. Okay, so starting at the 9-inch mark there on the ruler, I've made this one an actual inch apart. So we can see that that comes before this 10-inch mark on the ruler, and then again things just get out of whack. So here these yellow lines are uniform lines, each of 1 inch, according to the dimensions of the image itself. And they of course do not match the inch markers that we see on the ruler. Okay, so that's one thing. Now, also what I've done here is I've taken, I've put a mark on the 9-inch mark here and a mark on the 10-inch mark on the ruler here. So I've taken that distance and then I've repeated that distance here, and you can see already that it's gone so this distance is representing the first inch that we see, but then we can see that now it's gone to 11.5 inches here in this same equal space. So basically the same space that we have between the 9 and 10 markers now has more than an inch and a half basically. And then here we can see that it goes from 11.5 to 12.5, 13.5 to 14. So we've got even more space on the ruler compressed into this equal space here. And then again, there's a white line right at the top of the image here, another equal space. So here we've got 1, 2, 3, 4, 5 inches compressed into this space here, and so it goes on. So this is just to really illustrate how when we use some kind of uniform measurement of distance in our image, it doesn't fit with what we actually observe. Now what I've done here is now put these red lines on each of the markers. Let me just take off those spaces. So we can see now this very clear compression. So each red line is on one of the inch markers, and the further it goes into the distance, then the more and more compressed it becomes. So just bear in mind that this is what we see when we look across a surface, what we see when we look at the sky going off into the distance, and it's also what we would see if we were looking at a building. We're at the bottom of the building looking up, and we can see that everything appears to get closer and closer together. So again, that's why if we're looking at the sun or a star in the sky, we cannot really measure its physical distance. Yes, we can predict where it will appear. We can predict the angle that we would see it from the surface in any given location, but that does not tell us the actual distance. These are different things. So that really it should be a very simple explanation of the difference between tangible measurements made with a ruler, which if you're going to measure the Earth and assume that there is curvature, what you need is tangible measurements. But what we know is that we're actually on a level surface, and observations that are governed by perspective have been converted into this geometric, trigonomic, orthographic illustration of us being on a globe. So that is why perspective is the imaginary curve. Perspective and observations that are governed by perspective are not the same as tangible measurements. Okay, so to the globe earthers out there, If you want to prove that you live on a globe, you need tangible measurements. But at the same time, if you want to understand how we know that we're not on a globe and we are on a level plane, you just have to understand that all the observations made to assume that we live on a globe are governed by perspective, and it is perspective that has been converted into this imaginary curve. Thank you very much.
Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.